So we started considering stochastic differential equation. That is, we are looking for process psi that satisfy, for instance, something like this in an integral form. Well, we are going to work mostly in one-dimensional case. As we said, because one-dimensional case is, at least in the terms of existence and uniqueness, is very close to one-dimensional. And later we will need multidimensional case for some PDE connections, but it's going to come later. Multidimensional version of stochastic differential equation is written like this. So we have D independent Brownian motions, and we considered standard assumptions A2 and A1 and A2. I will only write them down in one-dimensional case. The first one is Lipschitz continuity. So there exists C for all x and y uniformly 0 of t. We have so-called Lipschitz condition. And the second is condition that of linear growth exists again C, again uniformly on T. Both coefficients grow at infinity, not quicker, not faster than linear function. In what follows, I will concentrate on the case where coefficients of the original stochastic differential equation do not depend on T. And it's pretty clear from the way these assumptions are formulated that it's not going to matter for existence and uniqueness. The calculation are going to be exactly the same. We will just need to write down every time this additional coefficient T. So we started proving the existence theorem. So assuming that A1 and A2 hold, and coefficients A and sigma are also they're not random. So nothing, we need nothing. There exists a continuous solution psi such that also for some C, even such supremum is square integrable. I started to making a remark that you can consider random coefficients by adding here omega and requiring A1 and A2 to hold also uniformly over omega, then everything also works, but we aren't into that case. So we already established two steps. The first step is how we define so-called Picard iterations. So in the very same way a standard existence theorem is proven for ordinary differential equations, we can define psi 0, psi n s dws. So obviously we are now going to construct our solution as the limit, appropriate limit of such psi n. And we also established that we can work in L2 omega because we proved that this is bounded. Now we can finish the proof by going to the step 3. But before going to the step 3, we will need to recall what Gronwell Bellman, or sometimes it's just the Gronall lemma is. We will use this extensively in this theory. So we will need to write down first few occasions very carefully and in full detail. So later we can just skip those details. Be non-negative bounded functions on, say, 0 t capital, and beta of t is less than alpha plus t plus c for some c, for c greater than 0, t beta of s ds. Then beta of t is less than alpha of t plus c integral from 0 to t e to the power t minus s alpha of s ds. So we get rid of beta. And in particular, and this is the case we are going to use almost exclusively, or maybe even exclusively, if alpha of t is just alpha 0 and a number, a positive non-negative number, then beta of t is less than this expression. So if alpha 0 is just 0, beta is also 0. I'm not going to prove this. This should be a well-known result if you do not know how to prove it in what has happened. In this general situation, you can look, for instance, for the book of SR course on Markov processes. It should contain a full proof in this general version. Because sometimes it's formulated when alpha and beta are continuous. Okay, I don't know what is happening, how I lost all my notes, where are they? They're here. Okay. So if beta is just, so again, if you wonder how to prove, or you can look at the proof when alpha beta are assumed continuous and just generalize it. It's pretty much the same idea. So the step 3 is going to be about estimating in square mean such expressions. So we are going to prove that our sequence of psi n's is Cauchy in some sense. So we know that this exists by step 2, so we can write it. And here we are going to set up our Gronall-Bellman. We will do it at least a few times very carefully. So I am, for psi n plus 1 at psi n, I am writing the representation, and I am estimating a sum of squares by 2 squares of separate terms. The sum of 2 times the sum of squares. A psi n of s minus a psi n minus 1 of s square ds. No, we cannot just write square here. Plus 2, 0 to t sigma psi n of s minus psi n minus 1 of s dws again squared. So recall that you can use the holder inequality to get something like 2. Now, let us assume that we use C to denote a constant that doesn't depend. Let us use C to denote a constant whose value changes from line to line, so I don't really need to care about its value, and I can forget about these tools. So claim, let's formulate this as a claim that psi n plus 1t x t square supremum is less than some constant that doesn't depend on n, integral from 0 to t. This is our delta n plus 1 of t, delta n of s ds. So let's prove this claim. So it's very easy by the Lipschitz continuity to see this for the first term. So let us concentrate on the second term of stochastic integral because it's always harder to do. Psi n of r minus psi sigma of psi minus 1 r dw r squared. So this is, I am just using this part, taking supremum and taking expectation. So this is less than, we had an inequality that estimates the supremum of a square of stochastic integral in the terms of the integral of this type. And we had, yes?
So in the claim, don't we need to write a constant plus there? Because by Groenewald lemma, I think this will mean that the difference is at 0.
Yes, but there is no constant anywhere. This is not directly a Groenewald. We will use it a bit later. Here, just this claim. I have this difference. They start from the same point. So their difference doesn't contain anything but a sum of two integrals.
Okay, thank you.
Mm-hmm. So here we have square here, dr, and now we can use A1, the Lipschitz condition, to conclude that this is less than some constant that depends, that comes from that Lipschitz condition, psi n r minus psi n minus 1 r squared dr, which is obviously less than if you write here a supremum over s less than r psi n of s psi n minus of 1 s squared dr. But then we can push this expectation inside, we are done. So we have that this is less than some constants. It doesn't depend on n because we never used anything n related. This is just the constant that comes from the Lipschitz condition. Delta n of s ds is less than c, integral from 0 to t capital. I'm making this integral larger. And now we need to carefully iterate this expression. Let's do it carefully. dt1 integral from 0 to t1 dt2 delta n minus 1 delta n minus 1 of t2. So I'm writing this firstly like delta and t1 dt1, and I'm using the same relation for delta n t1. Now we can iterate this n times, and we will end up with it n, exactly n, iterated integrals. Delta, and we have here 1, I think. T. But by the the second step, we know that this is bounded by some constant. So this is Cn delta 1 of t capital. And what is less we have here is an integral over a simplex, effectively. And this is just t capital to the power n divided n factorial. You can do it yourself. This means if we consider now such series, this is less than, by the Markov inequality, n to the power, no, we can do this, n to the power 4, mathematical expectation, sum s less than t capital psi n plus 1 s minus psi n of s squared, which is exactly less than sum n to the power 4 and 4 Cn t capital and factorial delta 1 of t. And obviously this is converging because we have factorial here, so these powers do not matter. Control D. Now, by the Borel-Coltelli lemma, there is a continuous and progressive, because it's limit almost surely, psi that psi n converges to this psi when n goes to infinity in uniform norm, in this sense, almost surely. Here. We started from here, so the Borel-Coltelli lemma says that starting from some point, these supremums of differences are going to be less than 1 over n squared. And that's what we need. That's the whole series are convergent. And again, this is because we can write our psi n and this sum. We already used something similar when we were proving the existence of integrals. And this series is convergent almost surely, as I said, because we have this here, the sum of 1 over n squared. It's convergent almost surely and uniformly on 0t. And we can then immediately also obtain this second estimate in the original proof. This is by definition what a norm in L2 omega is just norm L2 omega. L2 omega is Hilbert space even. Now this is limit when n goes to infinity, supremum psi n plus n of t minus psi 0. Now we can use the Fatuli lemma again. So this is less than infinitum and goes to infinity. Supremum psi n of t psi 0 of t. And the idea is because this can be written as a sum. Why? Because supremum t less than t capital psi n of t minus psi 0 modulus this norm can be written as a sum k n minus 1 those course supremum t minus psi n minus t. This is just the triangle inequality for a norm. But again, this is convergent. So this supremum is less than something bounded, which is exactly what we claimed in the original formulation. Why? Because then I can take this 0 from here, and this is less than some ct minus psi 0 squared t less than t capital plus 0 squared. And then we can use the estimate we just obtained. This almost surely is an ideal mathematical expectation and estimate this in terms of this number, which is finite. Now we are left with the final step. We need to prove that this is a solution. We constructed some Cauchy sequence, but we cannot just immediately conclude that this is a solution. We need to pass to the limit in the corresponding expression for psi n here. So here we need to pass to the limit with respect to n in the left-hand side, in the right-hand side. And obviously the left-hand side is going to converge to psi of t, but what we proved. And pass to the limit in the right-hand side, we need to consider integrals of this form. Plus double s squared. And using the Lipschitz condition, we will end up with something like psi n of t minus psi of t squared, which is again this norm. But we effectively just proved that this is less than capital psi j of t, psi j minus t out to omega. Because we're now starting from the nth point. Right? No, it's not right. It's not right. But we proved that psi n is the limit not only almost surely of for the sequence psi n ends, but also in L2, because we can also prove that psi n converge to psi C0 t in L2 omega. In the sense that supremums over t is also converging in L2, because this is the very same estimate of this type. We are going to estimate this in terms of the series of this form. So this goes to 0 and goes to infinity, and it allows us to conclude our construction. So we obtained a solution, proved that it can be obtained as a limit of good simple functions. Now we want to prove the uniqueness theorems. For that, we will need the following additional statement to the original stochastic differential equation, possibly with different starting solutions, starting points. Then the divergence in the uniform norm between two solutions in square mean is going to be dominated by what happens at the beginning. So we again define delta as a difference. Tau n is infinite of those t small that at least one of the processes hits higher than n capital. And now we can use the Gromov-Bellman lemma, because we didn't even use in this proof effectively. So I was too quick to introduce it. But for some reason I thought we are going to use it, but I just remembered the proof wrong because it didn't needed it. Now let's be careful. Let us consider delta squared of s, this supremum. This is less than the sum of two supremums. So I'm just writing the expression for xi, the expression for eta, taking square, and this is less than 3 times the sum of squares of such differences. T min s less than t minimum tau n, integral from 0 to s, a psi n of r, is a eta n of r, dr squared, plus 3 supremum s less than t and 0 to s psi r sigma and eta of r d double r squared. And now let us consider these two expressions separately. This is going to be eta 1, this is going to be eta 2, E1, E2. E1 by the Holder inequality is less than some constant, supremum, s less than t. So I'm using Holder inequality to push the square inside of the integral. So this constant is just 3 times, well, t capital or something like that. Yes. I'm obtaining psi of r minus eta of r squared dr. So is less than I'm pushing supremum inside. The integral from 0 to t, supremum u less than r minimum tau n delta UDR. And the mathematical expectation, I need mathematical expectation to work with the stochastic part, is less than, again, constant. Constant is equal 4. Indicator R is less than tau n delta squared R dr. Because everything happens until we hit this tau n, until we hit level tau n. And again, this can be estimated as some constant, mathematical expectation from 0 to t, supremum over u less than s minus tau n, delta squared of u ds. And now this gives us our Borel-Cantelli, Gronwall-Bellman inequality s less than t minimum tau n delta squared of s is less than c, this expression, plus both integrals can be estimated in this form. Supremum, I push expectation inside, less than r less than s minimum tau n delta squared r ds. Now this is our beta in the Gronwall-Bellman inequality. This is our alpha, which is just constant. So by the Gronwall-Bellman inequality, this supremum s less than t is by the Fatou lemma. We already used this a number of times. This idea that we can write this, estimate the supremum of the whole interval by the limit inferior of simplified s less than t tau n delta squared of s, but this is going to be less than some constant delta of 0 squared, which is exactly psi 0 minus eta 0 squared. So this is idea of introducing this tau n is something that persists through the whole theory. So it's often omitted in textbooks or in papers by just saying that we can use a standard localization. But standard localization means exactly that. You introduce something that stop processes that are stopped when they hit above some level. You write everything here because everything works here well. Everything is going to be more or less bounded or controllable. Then all integrals exist. And in the end, you will use the Fatou lemma. And this immediately leads to the uniqueness theorem. The solution to the stochastic differential equation we introduced at the beginning of our lecture is unique. Unique in which sense? That by the previous proposition, we can claim that mathematical expectation supremum s less than t capital psi 1 of s minus psi 2 of s squared ds is just 0, because psi 1 at 0 equals psi 2 and 0, and psi 1, psi 2 are solutions, which means that these two solutions coincide on the whole interval 0t with probability 1. And this is the meaning of the word uniqueness. They coincide almost surely on the whole interval. now a very important for us in what follows theorem is this follow localization. Let us consider two stochastic differential equations with, generally speaking, different coefficients, the same Brownian motion, same starting point, and coefficients are assumed to be compatible in the following way. For some n capital greater than 0, they coincide. I'm writing one-dimensional case. In multi-dimensional case, you will need a rectangle. Take this to the power equal to the dimension of the solution. And then solution coincide until they live inside of this. So if we start in the area where those coefficients coincide, if then for tau k equal infinitum, the first moment eta k leaves this interval, or just t capital if that doesn't happen, we have that these moments of time coincide almost surely and solution coincide on this random interval almost surely. Then they're going to be different because coefficients might be different. But solution to stochastic differential equation, exactly as solution to ordinary differential equations, are local. Again, set this difference, delta to be equal to this difference, and we can then have the following representation. Starting points cancel each other, and I am not writing S here to simplify notation. Sigma 1 eta 1 minus sigma 2 eta 2 dws. Now let us consider only the second integral because the stochastic integral is harder to do. So let me write it in this way. Eta 1 minus sigma 2 eta 1 plus sigma 2 eta 1 minus sigma 2 eta 2. So this is, I added and subtracted this expression, dws. But now sigma 1 and sigma 2 calculated at the same point, eta 1 of S, before eta 1 leaves this 0 t capital times minus nn, and this exactly happens only at time tau 1. So for all values of S that are considered in this integral, eta 1 lives inside of this region in terms of n capital, and that means that this term is just 0. So it's just integral tau 1 sigma 2 eta 1 of S minus sigma 2 eta 2 of S dws. Now we're going to take the expectation of the square of this expression, and in a very similar manner to what we already seen, this will lead to the following estimate for our difference, some constant, because it's going to work also for the first integral too. And I am going to add supremums everywhere. Tau 1 delta n ts. And then we can use again the Gronwall-Bellman lemma to conclude that this supremum is just 0. And this is our conclusion in the sense that that means that delta equals 0 on this time interval. Which means that eta 1 equals eta 2 before times t1, and tau 2 is greater or equals than eta tau 2 is greater or equals than tau 1. Theoretically, it can be greater because the value of our coefficients change exactly at this moment. But now we can write everything by switching the roles of eta 1 and eta 2. So we can define now new delta that equals eta 2 minus eta 1. We will arrive at the same conclusion, and we will particularly conclude that tau 1 is greater than or equal than tau 2. So switching the roles of eta 1 and eta 2, we get also tau 1 greater or equal than tau 1, which means that they coincide, surely. So why we considered this localization? It allows one to consider stochastic differential equation, for instance, with local Lipschitz coefficients, because then you will build your solutions locally. You will redefine your original coefficients in the way that they're Lipschitz on the whole space, build your solution for them, and then say that the for original stochastic differential equation is only local Lipschitz continuous coefficients. You can take until some moment as a solution, this solution for redefined coefficients. And then you can glue them together. We're using some Markov property we are going to discuss later. And also it allows one to consider stochastic differential equation without these assumptions on everything being square integrable. In particular, we already discussed on a number of occasions that one can define stochastic differential equation not in L2 sense, but in the sense of convergence in probability, and that allows one to extend the theory in that case. So for instance, A2, the condition of linear growth will be replaced by the condition of locally linear growth. So everything is kind of locally square integrable, but the whole solution might not be. Now it's time for us to look at examples. Overall, contrary to the case of ordinary differential equations, there is no general methods to solve stochastic differential equation, and the number of stochastic differential equations for which exact solutions are known is very low. We will consider some simple examples and some more involved examples. So we will be starting with ordinary linear equation. BWT. And the solution is psi of t equal psi of 0, mathematical substantial from 0 to t alpha s minus sigma squared of s over 2ds. I think, and this part, yes. dws. Well, you can check that using the eta formula, can consider this as an exercise. And an important sub example is if alpha is just alpha 0, sigma is just sigma 0, they are constants, then psi of t has a very interesting form. And this is called geometric Brownian motion. So this is a rare example when you can solve it directly. And sometimes, as we will see, it is possible to transform coefficients in a controllable way to get conditions that satisfy that fall into one of the cases where the solution is known. So sometimes it is possible to transform original coefficients to arrive at a linear SDE. You can check in most textbooks are going to contain a correspondence section, but we will omit that. Let us consider this stochastic differential equation. Then the solution is also known. It's going to be written as mu dws. This is a very important example because this is something that has a name. This is Ornstein-Uhlenbeck process. What is important about this process is that it's kind of a linear motion with some coefficients and some stochastic part. So this expression is often called the Langevin equation, the stochastic Langevin equation. Typically, this is considered for mu negative, but you can still obtain the same solution when mu is non-negative. And an interesting feature of this example is this is a Gaussian process. Why? Indeed, this is a constant function, a deterministic function. This is a deterministic function, and this is a stochastic integral of a deterministic function, a stochastic integral of a deterministic function, when this function is good enough, and this is a continuous function, can be obtained as a two limit of Riemann sums, but L2 Riemann of Gaussian random variables is again a Gaussian random variable. This is also an interesting example. This is a so-called Brownian bridge. So let's consider the stochastic differential equation with coefficients that do not satisfy really the assumptions we started with. 1 over t a dt plus dwt, where t lives from 0 to 1. So we have problems when t is equal to 1 because this becomes infinity. So firstly, let us just consider stochastic differential equation. This stochastic differential equation, consider this SDE on some subinterval where t0 is strictly less than 1. Then everything works fine, and we can define our solution. Because then both coefficients are going to be Lipschitz continuous when restricted to this time interval. So the solution exists, it's unique, and actually one can check what a solution is. There is a way to arrive at this conclusion, but we will just use it right away. So let us check that this is indeed a solution of the original stochastic differential equation. For that, we will use, obviously, the eta formula. This is AT. So this is deterministic part. So this is just going to be A minus psi of 0 dt. We're just differentiating with respect to t. Now we differentiating with product. This process is a deterministic product. So when we are going to apply derivative is going to give us just -1. And this is a stochastic process. So we're going to consider a derivative, a stochastic differential of this expression. dws 1 minus s. It can be seen as a stochastic derivative of f of t, g of t, where f of t is just a deterministic function 1 minus t, and g of t is a stochastic integral. So df of t is just minus dt, but dg of t is going to be a bit more involved. It has no derivative, so it's going to be dw to t 1 minus s, 1 minus t. That's all. That's all I was thinking. I was overcomplicating things, I think. dt minus 0t dws 1 minus s dt. So this is dft. dwt 1 minus t. We don't have the second derivative because g of t is just this stochastic differential equation psi of t. If you had, say, the square of this integral, we would have to correct the second derivative, but it doesn't even appear now. This and this cancels, and here let's say t minus t 1 minus t we need. A will give us what we need. It seems that we are right, because we started from here, a of t plus k is 0, 1 minus t. Yeah, it should work. It checks this as an exercise. So for any t0 less than 1, we have a solution. And we already know that they should coincide because they are unique. So effectively, we have a solution on 0, 1, excluding 1. And the question we are going to answer, whether we can define a solution also for this 1. Let us start by noting that psi on 0, 1 is a Gaussian process. Gaussian process. Mathematical expectation is going to be here, just this part, because the mathematical expectation of this part is 0. So it's going to be AT plus 1 minus t psi of 0. The covariance for this process cares only about stochastic part. dwr 1 minus r integral from 0 to s dwr 1 minus r. Now, let's recall that both these expressions are sums, limits of sums. And values of stochastic of Wiener process are independent on disjoint intervals. So this is going to be mathematical expectation of the product of these two integrals. But again, what happens, and let's assume that s is less than t. What happens after s is independent of this integral of the whole this integral. So that part is going to disappear and we will arrive just s 1 minus r squared dr, which can be rewritten 1 minus t 1 minus s, just integral from 0 to s minimum t dr 1 minus r squared, and then just know the answer because it's a standard answer. And I used Brownian bridges a lot in my life. So you can check that this equals to this expression. And now what we see is that mathematical variance psi of t is equal to t 1 minus t, and it goes to 0 when t approaches 1 from the left. And when the variance of a Gaussian random variable goes to 0, this means the Gaussian random variable converges to 0, to constant. So this means that psi of t converges to some limit that exists of mathematical expectations, and this is I. This happens in L2 omega. Thus it happens in probability. Thus there exists a sequence for any sequence of times that converge to 1. There exists a subsequence such that this convergence happens almost surely. But psi is a continuous function. So if this happens for this subsequence, it happens for the whole process. Because this has this simple expression where everything is continuous. So we can define psi of 1 as just as a. So despite the fact that we cannot use our existence theorem on the whole interval from 0 to 1, we can still define the solution, stochastic differential equation. And what happens is a well-defined Gaussian process because the limit is just a constant. And an interesting interpretation in the reason why Brownian bridging is important is the following observation. So let us assume that everything starts from 0. And let us ask yourself, what is the distribution of a Wiener process conditionally on its value at the terminal point of time? I'm not going to write down it explicitly, but for any t, this expression is a Gaussian distribution because you have a standard result from probabilities that conditional expectation of a Gaussian random variable variable with respect to another Gaussian random variable is again a Gaussian random variable. As effectively what we are doing, because Gaussian random variables are L2 and integrable, you are projecting in the Hilbert space of square integrables random variables one Gaussian random variable on another. And what is left, this beta is independent of W1. So this is a scalar product in L2. This is normalization. So this is the coefficient. And this is a projection of WT on W1 in L2 omega. And this can be calculated because this is just T W1 plus beta of T. So beta of T is equal T W1 minus D. But this immediately gives us the answer. So if we know the value of Brownian motion at the terminal point of time, we can just substitute it here in this expression. And what is left is independent. So this is going to give us our conditional distribution. But now one can check this is beta has the same first and second moments as our Brownian bridge, which means psi is effectively a Brownian motion conditional to hit A in the original formulation. This is the region where Brownian bridges are important. They give this conditional distribution. So we started with this stochastic differential equation and arrived at this interesting conclusion. Now we want to discuss the following question. As we already noted, sometimes it is possible to transform coefficients to arrive at something that is easier to deal or something that is very important. And we will consider only one case for that. dt plus sigma psi of t dwt. And first example on this route is going to be as follows. Let us find such f that the expression, when we substitute psi of t for f, does not contain ordinary integral. So we are looking for f such that we can get rid of the drift part. So what we need, f is a monotone. Second, derivatives with respect, there is no derivative with respect to t exist. So the Ito formula works. Exist the inverse function and dft psi of t does not contain drift. So let us write down the Ito formula. This is psi of t dt, a psi of t dt plus 1/2 second derivative psi of t sigma squared psi of t dt plus first derivative psi of t sigma psi of t dwt. And if f is such that this part disappears, so f prime x a of x plus 1/2 f 2 primes of x sigma squared of x equals 0, then for this stochastic process, and it's well defined, and because f is monotone and there is an inverse, we can always switch between eta and psi. We are going to have the d eta of t dwt, where this new sigma y is just here, look, sigma f minus 1. Why this is? So it is sufficient to find such f. And in this case, the answer is known. F of x is defined up to 2 constants, and it has a following form: 2a of z sigma squared z dz. And in the theory of one-dimensional diffusions, it's known as a scale function. And if this all works under much weaker assumption on a and sigma squared, essentially one just requires sigma to be positive and a divided by sigma squared to be locally integrable. That's a bit outside of the scope of our course. So this is a fast transformation that allows one to start with stochastic differential equation of a general form and arrive at something that contains only stochastic part. Now we want to discuss another transformation that allows to get rid of this sigma in the sense that we arrive at something that has just one for a coefficient. And for that we will need the following result. Unfortunately, it is a bit of a digression, but we cannot avoid it. And it simplifies further exposition significantly. So effectively, this is Levy's theorem on the characterization of the Brownian motion. And it's typically formulated in terms of martingales, but we will avoid that. So let's a progressive process be such that it's continuous. For every t, I said it's progressive, but it's not really needed. But maybe let's keep it just progressive. And we have the following two conditions, which effectively say that psi is a martingale with respect to our filtration, ft. But we are not going to use martingale techniques. And this is just h, again for all positive h. Then psi is a Brownian motion. So let's prove it. I will prove it. We will prove only the following. So for any t greater than 0, for any h greater than 0, We have this independence. And these two conditions are sufficient to conclude that we have a Brownian motion, regardless of the definition of the Brownian motion you are using. Because if you have independence, you can go for multidimensional distribution and use the tower property of conditional exploitation. You could use another trick, but this is sufficient. If you don't know this, use as an exercise. And return to the definition of the Brownian motion we gave at the very beginning and check that this is sufficient. And for that, it is sufficient to prove, say, the following. That this conditional characteristic function equals unconditional, the conditional one. Why? Indeed, if you just take another expectation, this gives us just a simple characteristic function. And this gives us the second property we want to prove. And secondly, for any delta belonging to Ft, we are going to have the following. By the definition, what conditional expectation is. And now one can say that one either can prove that the conditional distribution is now of this expression coincide with unconditional, or one can argue that this function can be used to approximate continuous function of this difference. Choose the method you prefer and do it as an exercise, but this means that psi is independent of the sigma algebra. So this was our first step. And let's do step 2. We will be relying on Taylor expansions that are used almost surely. So I will denote delta psi, this psi t plus h minus psi of t, and let us consider the difference of what we have and what we have to obtain. We will consider decomposition up to order 3, I think. E lambda delta psi. Recall that this is sine lambda delta psi. So sinus is going to give us minus I lambda squared delta psi squared alpha squared divided sin where alpha is a random variable such that is measurable. This is what here, this gives us just lambda squared delta psi squared over 2 plus lambda squared h over 2 minus L squared h plus, I'm too lazy to calculate. I think it's one. It's 6 factorial times 8. So it's 48, but let's just put some constant. Lambda to the power 6, h to the power 3, some beta, where beta is some number from 0 to 1. So what I effectively did here, I just, for instance, wrote down this expression, and 1 is lambda squared h2 plus lambda 4 h squared 8 minus 1 2 to the power 3 lambda squared h to the power 3 beta. So it's just a Taylor decomposition of what we have here. Because 1 minus x is x minus x squared 2 plus 3 and some beta. So we have a sum of 4x terms. And the idea is to prove that this difference is of order strictly greater than h. So we can get rid of it after dividing by h. Now, why this expression is measurable? We already, because if you look at the Taylor decomposition, you will see that the last term can be expressed in the terms of the previous term of the original function, and everything up to that moment is going to be a random variable. So this must be a random variable too, and because this alpha is included here in a very natural way, alpha is also should be a random variable. So effectively, if you're taking this conditional expectation, this will get rid, for instance, from this term, because our condition just directly says us this is going to be 0. So we will write minus I lambda squared 6 alpha delta psi squared ft, and plus I will write this O small of h squared. So we will need to estimate this expression. Lambda is fixed. Alpha we do not care because we will be estimating this using modulus. So this is less than by the Holder inequality. To the power 3/4. So step 3, we are going to prove that mathematical expectation of this expression is less than some constant h squared. So this will give us then some constant h to the power h squared 3/2. For that, let us proceed as follows. Let us introduce this uniform partition of the interval from t to t plus h. Delta g is going to be, one moment, I'm sorry. And then delta xi is the sum. Delta k. Now we want to consider the fourth power of this expression. This is going to be delta k to the fourth power. The idea is we are going to estimate it in terms of some summands. We will get rid of some summands, and what is left is going to be positive, and we will apply a conditional for 2 lemma, but let's be careful. So I am calculating y square and writing it in this form, g. So this gives us squared plus 4 k less than k delta g squared plus what happens when we multiply this and this, g l less than g delta g delta l. Now here I do not want to touch this expression. It's already positive. It is squared delta k delta g squared. Here I will going to write this delta 4 to the power k plus 2 sums k, exactly as we did previously. J, all right. And I want to decompose this expression into 2 sums. So the first star part will include the case where we have something k equals j. So effectively is just the sum L less than k delta to the power 3 delta L plus what happens when k doesn't equal j. Then we have k not equal j and L is less than g and L also doesn't equal k, delta squared k delta g delta L. Now everything that is not guaranteed to be positive, that is everything except for these 2 terms, must go. For that, the following trick is used. For any c greater than 0, probability that this is greater than c is less than c minus 1 just by the Markov inequality is the sum. And now we can use the assumption of the assumption, and this is less than sum h over c, so this goes to 0 and c goes to infinity in particular. And that means that for any epsilon, is less than just squared times maximum over j delta j to the power epsilon. This goes in probability to 0 because it's bounded in probability. So this goes to 0 and this is bounded and everything goes to 0. And that means that this expression and expressions that contain second of this type converges to 0 in probability. And for instance, along some subsequence. So if we return to this expression, This allows us to get rid also from this term, And what we're going to do with this term, so this is limit along some subsequence. This is going to converge in probability, so I will switch to some subsequence everywhere. This is limit almost surely of what is left. This is this expression we didn't touch, delta k delta j squared plus we have this part. Now we have this part and this part plus 2 some k j less than k squares. This part plus this. All coefficients are different and L is less than J. All coefficients are different and L is less than J delta squared K delta J delta L. And now I want to get a square here. To sum over K. I want to have something J. Let's see where we can do this. Something like that, I think. So this is sum, this is sum. We are running out of time, and so we will stop here and continue from this point next time. Does someone have any questions? Okay, then I'll see you next time.